All right, today we're diving into something that sounds like it's straight out of a science fiction novel, but is getting closer to science fact every single day. We're talking about quantum fractal alloys and how we can use the strange, infinite complexity of geometry to literally engineer the materials of the future. So, let's just start with the big question that's really pushing all of this forward. What if we could stop just finding new materials and start designing them from the ground up? I mean, imagine materials that can literally change their properties on command, materials with impossible strength, materials that could even protect the fragile world of quantum information. Well, that's the wild promise behind quantum fractal alloys. And just to be clear, this isn't about making a slightly stronger, slightly lighter version of something we already have. Nope. We are talking about a fundamentally new class of matter. And the key to its almost unbelievable properties isn't in its chemistry, but in its geometry. So, what's the big promise here? Well, for starters, we're talking about materials that could be stronger and lighter than our best superalloys and can handle insane amounts of heat. But the real game changers? The ability to switch from a conductor to an insulator in a blink, and the power to naturally shield fragile quantum states. And that is a huge deal for quantum computing, because right now, outside noise is one of the biggest roadblocks we have. Okay, so how is any of this even possible? Well, the secret sauce is what happens when you smash two mind-bending fields together. The bizarre rules of quantum mechanics, the physics of these super, super small, and the infinite, intricate beauty of fractal geometry. This slide lays it out brilliantly. On the left, you've got your normal material, atoms in a nice, simple, predictable grid. But on the right, you've got a fractal structure. It's this complex pattern that just keeps repeating itself on smaller and smaller scales forever. For an electron trying to move through that, it completely changes the game. Suddenly, the path isn't a straight line. It's a crazy, complex maze that forces the electron to behave in some really powerful new ways. To really get this, we have to talk about something called a fractal dimension. A line has one dimension, a square has two, but a super complex fractal pattern, kind of like the coastline of a country, is more than just a line, but it's not quite a full 2D space either. It can have a dimension that's a fraction, like 1.26. For an electron, moving through a space with a fractional dimension fundamentally changes its energy and its behavior. And that is the key that unlocks all these new properties. So this intricate, repeating geometry has this incredible effect. It creates, essentially, a natural fortress for electrons. It's like a hall of mirrors that shields them from the noisy outside world. This effect, which scientists call fractal confinement, is exactly the kind of protection you need for those super delicate quantum states in a quantum computer. So this all sounds fantastic in theory, right? But how do you actually test it? It's not like you can just build one of these things atom by atom, at least not yet. So instead, scientists build it inside a computer. They use a simplified model called the fractal quantum wire to see if the physics actually holds up. And what the simulations found was pretty remarkable. Take a look at this table. It shows the energy of an electron that's trapped in this virtual wire. Notice how as we make the fractal more complex, as we go from iteration 1 to 3, the energy of the electron goes up in a big, and more importantly, a predictable way. That's something you just don't see in a normal material. So, what's the big takeaway? It means we could potentially engineer a material's electronic properties just by tweaking its geometry, its fractal depth, instead of changing its size or its chemical makeup. I mean, that just turns material engineering completely on its head. And this idea leads directly to a really cool application. The simulations actually predict that a fractal wire could act as a totally new kind of transistor, the little tiny switches that are the building blocks of all modern electronics. And this chart shows that it works, at least in the simulation. With no magnetic field, the conductivity is high, the switch is on. But as you crank up the magnetic field, that fractal geometry causes the electron's own quantum waves to interfere with each other, basically canceling themselves out and shutting down the flow. The switch flips off. It's a transistor that operates on a purely quantum geometric principle. How cool is that? Okay, I know what you might be thinking. This all sounds incredibly futuristic, and honestly, the inspiration for some of this stuff comes from some pretty out there sources. But now, we're going to make the most important connection in this entire explainer. We're going to ground this radical theory in real, verifiable science. This slide right here is the anchor for everything. On the left, you've got the speculative origins, fictional ideas like the Magenti equation from the Stargate universe or the made-up alloy Nyrite. These were the creative sparks that made researchers ask, hey, what if? But on the right, you see the real-world science that gives this idea legs, established concepts like high-entropy alloys, and the actual nanotechnology research happening at world-class institutes like Mesoplus. This is the bridge from science fiction to how-to. And this isn't just theory floating around in a lab. There's a real-world ecosystem in the Netherlands that's already working on the building blocks. You've got the Mesoplus Institute doing the fundamental research. You've got companies like Lyonix and Quix building the actual quantum hardware that proves these geometric ideas work. And then you have huge industrial partners like Thales ready to apply these materials in aerospace and defense. It's the whole pipeline, from the lab bench to industry. So where do we go from here? This isn't just some random shot in the dark. There is a clear, methodical roadmap for turning these incredible simulations and theories into reality. It's basically a three-step journey. First, the researchers have to perfect their computer models, make sure they're totally stable and accurate. Second, they'll benchmark those models against other methods to prove they're on the right track, and then scale them up. And the final, most crucial step is to create this feedback loop, feeding real-world experimental data from the labs back into the simulations to fine-tune them. It's this constant back and forth between the computer model and the real world. And that brings us to the final thought. This research, it really represents a fundamental shift in how we think, a move away from just discovering materials to actually designing them with purpose, atom by atom. So the final question isn't just for the scientists, it's for all of us. What are we going to build when the materials we use are limited only by our imagination?